Good afternoon to you all pre-matriculants. My name is Abram and we're in for a lovely show to learn more and learn extra together. And our lovely teacher, Mr. Tinyiko, how's it, sir?
I'm good, and you?
I'm also good, sir.
Yes.
Navula Shlungu
It's
namuhla.
all right, Bashlung
Ibashlungu
Namut,
ko.
it's physical sciences, here, chemical change, and of course, energy involved during a chemical process.
Nice one. I can't
Yeah.
wait for this show. Well, I must tell the mindsetters to get in touch with us. They must go to facebook.com/learnextra. Like the page, share the page with everyone. Involve their class teachers. And I believe that as a teacher as well, it's very useful. The learners, we should encourage them to bring their teachers on board as well.
That's a norm. That is what it should be. It should always be like that. Learners have to make sure that they are with their teachers. They know their teachers. They can actually interact with them.
But I must say,
Yeah.
sharing the information won't get you more marks or extra marks than anybody else. Well, also on Facebook, on Twitter, follow us at LearnExtra. Remember to go on our website for the schedule and the notes, which is learn.mindset.co.za. On the links that are provided for you and posted for you on Facebook, there's a test yourself link with questions. If you answer them, you stand a chance of winning this awesome Casio calculator. I'll be announcing last week's winner during this show. So guys, get on our page, share your comments and your questions that you have will help you.
Yes, thank you, Abram. And
Yes, sir.
now we kickstart our lesson. Like I said, we're talking about energy and chemical change. This has to do with what happens when those chemical reactions take place. We go deeper into the microscopic level where we look at how the energy changes are happening, how these atoms and molecules interact with each other energy-wise and are able to move from reactants to products. And of course, as scientists, we are actually looking for that product. We will do everything we can to allow these reactants to interact together, bump against each other until we get the right orientation for them to have enough energy to be able to give us or yield the results that we are looking for, which is ultimately our product. Okay, so it's about energy and chemical reactions. So we're going to talk specifically about this energy change, how it happens in chemical reactions. We are also going to define what we mean by an exothermic reaction as opposed to endothermic reaction. We're also looking to talk to what we call the bond energy. What is this thing here? We're going to explain it. We are going to discuss change in enthalpy, and I want you to note this thing here, enthalpy, change in enthalpy, and I'm going to go a little bit deeper into it as well. We are going to define what we mean by the activation energy and what we call the activated complex. We're also going to discuss potential energy diagrams. And of course here, potential energy diagrams, chemical potential energy of reactants and products. That's what we're going to discuss at that level there. All right, as usual, here is your challenge question. When sodium bicarbonate dissolves in water, the temperature of the solution formed decreases. In other words, if you're touching that beaker where this solution is, you are going to feel cold. Is this chemical reaction exothermic or endothermic? You don't just have to choose whether it's endothermic or exothermic. You pick your answer, you say it is exothermic or you say it is endothermic, and you explain your answer. So we need an explanation for that question there. Right. Energy change. Whenever a chemical reaction takes place, there would always be change in energy of the system. An exothermic reaction is a reaction in which more energy is released than absorbed. So you've got more of the energy that got in than what is given off by that process. For example, if you look at the reaction between methane and oxygen, this is a combustion reaction to give you carbon dioxide and water. This reaction is such that as it occurs, part of the product is energy. In other words, energy is given off. Okay? Energy is released. Okay? Now, if energy is released, we say the reaction is exothermic. Now, if we're talking endothermic reaction, this would be a reaction where more energy is absorbed than it is released. And to give you an example for that, we're looking at the reaction between the glucose molecule for oxygen, okay? In fact, we're looking at the reaction between carbon dioxide and water. And of course, you need a lot of energy here, and this energy is usually or is actually provided by the sun. We call it radiant energy. And that energy is supplied into this process, the photosynthesis process, for us to be able to form glucose and oxygen. So you would see that that's what makes plants very important to us, because during that process, the part of the product, it's oxygen, and we need oxygen in our lives to breathe it or taking it in, and for our own well-being. So it's necessary for us to have more of these plants around us, okay? So glucose, the starch that is formed, the food that has been formed by the plants, okay? In this process, energy is taken in, and when energy is taken in, we say that that reaction is an endothermic reaction. It takes in energy. There's more energy absorbed than it is released. Okay, now quickly, let me talk to this concept here called enthalpy. What is enthalpy? Enthalpy is the total amount of chemical potential energy in a chemical system. All right? During a chemical reaction, this enthalpy would change. Okay, and how does it change? We know that either that you're going to have more of the energy absorbed than it's released, or more of the energy released than absorbed. The change in enthalpy is given by the symbol delta H. Okay, some people, or in some books, it will be referred to as the heat of reaction. Okay, so we can refer to delta H as the heat of reaction. Okay, now for an exothermic reaction, we would have delta H, or change in enthalpy, being negative, meaning that there's more energy that has been given off than it has been absorbed by the process. Whilst for endothermic reaction, we'll have our change in enthalpy, or change in heat of reaction, greater than 0, meaning that more energy has been absorbed than released. Okay, now moving on, bond energy. What is this thing called bond energy? During a chemical reaction, energy is needed, okay, to break the bonds. This energy is taken in by the reacting substances, okay? And when new bonds are formed, okay, at that time when the new bonds are formed, energy is given off, okay? So formation of bonds involves two things mainly. In that reaction at the beginning, you've got bonds that are getting broken so that they can give way for new bonds to be formed. And when new bonds are, or the bonds are being broken, you need energy for that process to take place. You supply energy to get the bonds broken. And when new bonds are being formed, energy is released, okay, for new bonds to be formed. Right, so we have got energy coming in and energy given off in that process. The energy which is absorbed when bonds are broken or released, when new bonds are formed, it's known as the bond energy. So that is the bond energy that we're talking about. Now this energy change is given by all the energy absorbed to break the bonds minus the energy that has been released during bond formation. That formula there is very important. And down here, I've got a table that shows us, okay, that gives us a summary of what the bond energies are like. If I've got a hydrogen-hydrogen bond, that's how much energy I would need to break it, and that would how much energy will be released if H2 is formed. In that way, so you can go to any substance here, for example, the HCl bond. That amount of energy will be given off when the bond between H and Cl is formed. And the same amount of energy will be released when that, the same amount of energy will be needed to break that bond if that HCl is involved in a chemical reaction. Because in a chemical reaction, firstly, bonds have to be broken. Okay, so that table there helps us with that. Right, moving on, activation energy and activated complex. For a reaction to happen between two substances, a minimum amount of energy is needed, is absorbed to break the existing bonds of the reactants. This minimum amount of energy is called the activation energy. When this minimum energy has been absorbed, the reactants form a substance known as the activated complex. Okay? And the activated complex is a temporary but very high energy, very unstable state between the reactants and the products. So it is at that time when we are just about to form whatever intended product we wanted to form. Okay? At that moment, we say we've got an activated complex. So at that point, the new bonds can begin to form. And when the new bonds begin to form, you're going to have a drop in energy because energy is going to be released. Okay? It doesn't matter whether you're talking exothermic or endothermic reaction. When new bonds are formed, energy is going to be released. And we're going to see more of this as we proceed. Okay? Right, now, coming here. Potential energy diagrams. If I have an exothermic reaction and I've got potential chemical potential energy on my vertical axis and the course of reaction here, I'm looking at how the reaction takes place. There is my reactants. I apply or bring in the minimum energy required for this reaction to take place, which we call activation energy, to break all the bonds. From that point, I will form what we call the activated complex up there. Then energy is released, okay, as new bonds are being formed. And then the new bonds are formed, and I've got a new product there. In this case, it's a water molecule that is formed, okay. You would see that for an exothermic reaction, delta H is less than 0. It is negative, okay, because the energy of the product, which is somewhere there, it's much less than the energy of the reactants, which is there. And here I'm referring specifically to what we call chemical potential energy, okay, of the substances. Right. Now, if you look at this here, the reactant going to the product and energy is being released there. And if we were to put an amount to it, say about 20 kilojoules of energy have been released per mole, we would have that, and our delta H, of course, or the heat of reaction, will be minus 20 kilojoules per mole. So that's what we have for exothermic. If we look at endothermic, the same thing, we still have the activated complex after applying our activation energy there, and then that is our chemical potential energy. Reactants there, but look at where the energy of the products are. Okay, reactants there. The energy of the product is greater than the energy of the reactants. And for that reason, your delta H, is greater than 0. Okay? And therefore, delta H in this case, actually, it should be a plus 20 there, positive 20, meaning that your delta H is greater than 0. Okay, greater than 0, meaning we're talking endothermic reaction. Catalyst. What does a catalyst do? Or what is a catalyst? A catalyst can increase the rate of reaction without being consumed by the reaction or taking part in the reaction. So a catalyst is a substance that speeds up the rate of reaction without itself taking part in that reaction or without itself being consumed in the process. Okay, so that will be a catalyst. If I use a catalyst in a particular reaction, what does it do? Can I represent that symbolically using a graph showing how a catalyst works? Yes, the answer is yes to that. I can have my chemical potential energy graph versus the rate, the cost of reaction, and I can show that if I start with reactants there and I have the products there, well, this is an exothermic reaction. I can see that straight away. But the issue is here. When I introduce a catalyst, you would see that the activation energy before catalyst is that one. But when I introduce the catalyst, my activation energy is that. Okay, so let me just do that. My activation energy will be this one. That's what my activation energy is when a catalyst is used, so with a catalyst. Okay, now what has the catalyst done here? The catalyst has actually lowered the activation energy, EA. It has brought it down. Okay, so instead of needing that much energy for this reaction to take place, you would only need that much, the little amount of energy as compared to the original one. That's what the catalysts do, lowering the activation energy. And some books would talk about lowering the energy hill. Well, this is when you try to make science related to everyday life, that if you've got a huge hill, if you flatten it, it becomes less, and it becomes easier for people to actually climb and walk across it. Well, you can use that analogy, but then the concept is there. It lowers the activation energy, not energy hill. I wouldn't really encourage this part here, although I know they are there in books. A catalyst lowers the activation energy, but does not change the change in enthalpy. You can see that delta H there, that has not been changed. Okay, so that is what the catalyst does. It is very important to note that the use of a catalyst will never change the heat of reaction. It won't change delta H, but it will change only, it will have an effect on your activation energy. It lowers it, brings it down, so that more and more molecules can be able to react, because this time you need less energy to get your molecules to get to that state, what we call the activated complex. Well, let me leave it at that point. I'm going to hand over to Abram, and we're going to continue once again when we come back from the break.
Thank you, Tinigo. And Mindsetters, thank you for your questions and your comments on the page. If you're late, tell all your friends to brief you on what has been happening, but also let's help one another on the page. The challenge question is there for you guys, and the test yourself is there. We'll see you after this break. Welcome back, Mindsetters. I see you guys on the page, which is facebook.com/LearnExtra. Some of your comments and your questions. Let me just read these two. Gift Bafana and Chabeleng saying, I hope I'm not late today. Afternoon to all pre-matriculants, of course, and you too, Abram. And this one, Bonola saying, hi, AB. So far, so good. Sir is doing a great job. And can I please send a shout out to all my classmates, 11A from Topaz Secondary School. Guys, just send in your questions.
Topaz.
Do you know the school?
Yes, I know the school.
Okay,
yeah.
well, a shout out to all the learners from Topaz Secondary School. Yeah. Well, guys, we've got amazing prizes for you. We've got airtime proudly sponsored by Vodacom. 60 55 rand airtimes, but already we've given other vouchers, so you still can enter to win that airtime. All you need to do is to share the post that is posted, pinned on top on our Facebook page. Enter on our Curo, register and use the code, which is LEARN, LEARN. lowercase or uppercase, it's up to you. As long as it's Learn, register, like your favorite teacher, and then vote for them on Facebook, and you could win one of 4 Sonia Spire L cell phones that we have already. One is won, so we've got 3. Guys, get entering. Over to you, sir.
Thank you, Abraham. Let's move on. We've got some questions now to look at and practice and see how we are supposed to answer questions based on what we've just done, the lesson that we had today. Here is a question here. All right, it says use the table table of bond energies to calculate delta H. So we're going to calculate for delta H for the following reaction, okay? We've got a reaction between hydrochloric acid and bromine, so that should be Br2 as you always know it. It should be like that, right? And Cl2 the same way. Now, when that reaction takes place, we're forming HBr and Cl2. Is this reaction exothermic or endothermic? So first thing, let's find out the energies. What I did, okay, was to go back to the table and find out the bond energies from the table so that we don't have to flip all the time and waste time. But then let's go back to the table because you are to use it. So for this question, you would be provided with this table here. For example, look at it. I've got HCl, so I would take that energy there to break that bond because that bond is going to be broken. It's part of the reactants. Part of the reactant, I've got HBr, this one here. So that's the amount of energy is going to be broken. We need that energy to break that bond there. So I've taken that, I placed it on that page there. We also know that chlorine is going to be formed, so that amount of energy is going to be released per mole of Cl2 formed, and bromine, okay, that amount of energy will be released per bond of Br2 formed. Okay, now let's just move on to the question itself now. So these are the energies that you see there, okay? Now let's move on. It is per mole, so if you look at this reaction, I've got 2 moles of HCl reacting with 1 mole of that. So energy of reactants would be equal to 2 of what? The HCl, the energy is that one. You need 431 kilojoules to break 1 mole. So if I've got 2, I'll need twice as much. Plus, for Br2, I need that amount of energy to break that bond. So it will be plus 192. Okay? So that will be the energy of the reactants. And for me to get that, I can just quickly make use of the calculator here. Let's use it. I've got 2 times 431. Okay? Plus 192. Okay, so I need 1054 kilojoules of energy. Okay, so it's 10 or 1054 kilojoules of energy. Okay, needed here. Now, for the products, I've got this. So I'll say enthalpy that would be released by the products. If you look at the products, I've got 2 HBr, so it will be twice the energy needed or the energy released when the bond between hydrogen and bromine is formed. So it will be 368 plus Cl2, 1 mole of that. And then with Cl2 from our table, what do we have? Cl2 is 243, so we'll say plus 243. And what will that be? Quickly, let's make use of a calculator. Okay, so I've got 2 times 368 plus 243. And what do I get? I get 979. 979 kilojoules. Then this is actually kilojoules per mole, okay, for every mole formed or broken. Now, change in enthalpy, okay, should be equal to. Now I want to take you back to the formula so that we see where all this come from. Look at this. Energy change, which is this one here. Energy change here. It's given by energy absorbed minus energy released, okay? So my energy absorbed is the energy that was used to break the bonds, okay? So energy, total energy absorbed minus total energy released, okay? So that will be equal to, absorbed is 1054 minus released, it's 979. And then this works out to be, use your calculator quickly. So you've got 1054 minus 979. What's your answer? It's 75. So you've got positive 75 kilojoules per mole. That is the difference between the energy absorbed and the energy released. Okay, now if you go back to the question here, it also said to us, or wanted to know from us, is this reaction exothermic or endothermic? Now from the change in energy, you can tell that the reaction is endothermic. Why endothermic? Because the change in energy is positive. Okay, so we've got a positive overall change in energy. Right. Now, coming to question number 2. Let's have a look at question number 2. Question number 2 says, in the following energy profile diagram, the x-axis represents the extent of the reaction, whilst the y-axis represents the energy of the reactants or products. Okay, so there is the graph there. 2.1, provide names for labels 1 to 4. Now let's have a look at it. Look at number 1. What is number 1? 1 is your activation energy. That is the energy, the minimum energy required, okay, to get that reaction to start going. Activation energy. Number 2, you look at number 2, that is number 2. That is your delta H, okay? So delta H, or you can also say this is the heat of reaction, okay? Right, and then 3, where is 3? You look at 3 there. Wow, this equation here, or this chemical reaction here, we need to be careful about. Look at that. There is a double arrow there that tells us that the reaction is reversible. The reaction is reversible. And because it is reversible, it means it can go backwards. These 3 here, 3, you can tell if these now become the products and, the reactants, and A and B are your products. It will mean that 3, it's your activation energy. Again, now activation energy, you can be specific and say activation energy for the reverse reaction. Okay? Activation energy for the reverse reaction. And that would mean that even for the first one there, we can actually go there and be specific as well and say, this is activation energy for the forward reaction. Forward reaction. Okay? So in that way, we would have answered our question fully. All right. So that was number 3. Number 4, what is number 4? Number 4, it's that point there. That is where you have your activated complex. So number 4 represents your activated complex. Right. Calculate the activation energy for the forward reaction shown on the graph. Now look at it. Activation energy, reactants start from there, activated complex at 600. So the activation energy is equal to energy of the activated complex minus energy of the reactants. Energy of the reactants. So that will be 600 if you look at that diagram minus 100, and that equals 500, and this is given in kilojoules per mole if you look at the vertical axis here. Okay, kilojoules per mole. Right. Now moving on, 2.3, calculate the overall enthalpy of this reaction. Okay, now delta H would be equal to energy of products minus energy of reactants, and that will be equal to, if you look at the energy of products, they are at minus 150, energy of reactants at positive 100. So products minus 150 minus plus 100. This will work out to give you minus 250 kilojoules per mole. That tells you that this reaction is, of course, exothermic. All right? It tells you that. I wasn't asked to do that, but that tells me that's what's happening. Now, draw a sketch to show the effect of a catalyst, okay? We know with the effect of a catalyst, if I'm going to use an exothermic type of a reaction, okay, and exothermic type of reaction, okay? So reactants there, products there. If I supply a catalyst, the catalyst will lower the energy yield. But I need to be conscious, because it is only lowering that energy yield. It is not going beyond this, because it can't lower and it can't have an effect on the delta H. It can't have an effect there. It can only have an effect on the activation energy there. Okay, so if you look at this, you can say that was the starting point. So look at how much energy is needed now as opposed to the total amount of energy needed earlier on. So that is your activation energy. It lowers, all right, lowers the energy, the activation energy. Let me draw it like that so that this is let me show it nicely here. All right, so I have it like that. Okay, so that is how the energy will be affected. Okay, so you can say that is chemical potential energy and how the energy yield is affected in that way, right? So moving on, let's have a look at this question here, question number 3. During the process of cellular respiration, glucose is broken down to form carbon dioxide and water according to the following equation, okay? So glucose now is broken down. This is actually a combustion reaction. The reaction is catalyzed by enzymes. So what do enzymes do? They act as catalysts. The change in potential energy during this reaction in the human body is illustrated in the graph below. Okay, there we go. We have the graph there. Use the graph to answer the following questions. Is the breakdown of glucose an endothermic or an exothermic reaction? All right, give a reason for your answer. This is an exothermic reaction. Why? Exothermic. Why? If you look at this, that is energy of product, and that is energy of reactants. So delta H here is less than 0, and that is the reason. Delta H is negative, or you can just say delta H is less than 0. Okay. And 3.2, explain. Okay, explain how the enzymes influence the rate of the reaction. Okay, enzymes in this case are acting as catalysts. Okay, that is what they are doing. So if they're acting as catalysts, what are they doing? They speed up the rate of reaction. Speed up the rate of reaction. If you want to be specific, you would say they speed up the rate at which glucose breaks down to form, okay, carbon dioxide and water, or burn in oxygen to form carbon dioxide and water. Okay, you can actually say that. That is what it is happening, and that is what the role of the enzymes is there. So basically, this is about energy changes in the chemical reaction, the type of energies involved, delta H, chemical potential energy, enthalpies, and of course, the issue of catalyst, where a catalyst is used to speed up that rate of reaction. Good. Now, let me hand over to Abram. I believe you might be having some questions as well, so we'll look at them when we come back.
Indeed, we will. And Matitas, do also send us your challenge question answers on the post for the challenge question. After the break, I'll be announcing the Casio Calculator winner from last week's show. Stay tuned. Welcome back, Prematrix. Now, the moment that we've all been waiting for to hear the winner for our Casio Calculator from last week's show. And the winner is...
Who is that?
Tabiso Mabula. Congratulations to you, Tabiso Mabula. This awesome Casio Calculator is coming your way. But now, before I hand over to Tinyiko, I've seen your questions, guys. There's just this one comment saying, "Hi, Abram. I'm enjoying the show. Though I'm new on the page, my friend in school introduced it to me as I was asking her how she knew stuff before us. She told us her secret, and now I'm tuned in. Grade 11 physics. I'm so happy. Welcome, Wendy. Mwanama, welcome, and also share the secret."
Yeah, welcome, welcome. Share it to as many as you can.
That's what
it's not a secret anymore. Mindset is rocking. It's out there for you guys to learn. Okay, we're coming to the challenge question now. Okay, the challenge question for the day was saying, when sodium bicarbonate dissolves in water, the temperature of the solution formed decreases. So another way of putting it is to say the temperature of the content of that solution actually decreases, meaning that it gets colder than before. Okay, and what does that mean? And then if we say something is colder, it means when you touch it, you feel you don't feel warm, you feel cold. That coldness is felt by you. And what actually happens? What is actually happening for you to feel colder than before? Okay, let's just have a look at this. The question is this chemical reaction exothermic or endothermic? And explain your answer. Well, the very first thing we need to say or to note here is that this reaction is actually endothermic. It is endothermic. Why do we say it is endothermic? Because if I touch something and that something feels cold, it means that this particular thing is drawing energy from me. I am part of the surrounding. So energy is being drawn from the surrounding by this container where this reaction is taking place. Now, if it is taking in energy from the surrounding, a chemical reaction that takes in energy is known as the endothermic reaction. So it is an endothermic reaction that is happening here because it takes energy, or it takes in energy from the surrounding. Okay, the fact that we're feeling cold, it means that energy is being taken out from us as part of the surrounding into the system. All right, so this is an endothermic reaction. I hope everyone got that right. I mean, understand it. If I feel hot, it means whatever I am attached to, whatever I am leaning to or I'm in touch with, that thing, it's releasing energy. And that's why I am feeling warm from, I actually feel that this thing is warm and as compared than it's compared to me. Actually, if I feel warm when I'm touching something, it means I am colder compared to that thing. If it is warmer, it means it's releasing energy into the surrounding. I'm part of the surrounding. That would mean exothermic reaction. This one is not releasing energy. It is feeling colder as I touch it. Why? Because it's taking energy from the surrounding. I'm part of the surrounding into the system. So it is an endothermic reaction. I believe we've got some questions there that we need to deal with.
And congratulations to everyone that got it right. I'm sorry if you got it wrong. Next time, try again.
Yeah.
Right. First question. Okay.
Yeah. Let's see.
This one it's from Gift Bafana and Chabeling.
Okay.
How delta H is calculated? I didn't get that part clearly.
Oh, from maybe let's go back. Was that question? I think that was question number 1. Was it question number 1, where we calculated for delta H? Okay. This is when we're going deeper into the microscopic level. What's his name again?
Gift.
And therefore, here we're looking at what happens actually when we say, when you supply that activation energy, the duty of the activation energy is to break the bonds. So when you supply that energy in a specific reaction, if you've got oxygen involved in that reaction, you need to break the bond between O and O. Oxygen and oxygen, so that the two atoms of oxygen are free to react on their own. So that amount of energy that has been used to break that bond, we take it in. It's part of the energies we're going to use. Just like here, we had HCl, we had Br2, there is HCl. The energy needed to break that bond, we had to take it in because that was the energy that we had to supply. But when HBr was formed and Cl2 was formed, this would be energy that has been released, so we'll have to subtract those energies there. Now, how do we find those energies? We're going to go back to the table, okay? In other words, for this chemical, or for this reaction here, or for this question here, you will be supplied with that table that will tell you how much energy is needed to break a particular bond, how much energy is needed to or is released when a specific bond is formed, so that you can calculate for that delta, for changing energy. But then in a situation where you are just given the graph like that, energy changes, okay, given to you in a graph like this, potential energy versus the progress or the course of reaction. All you need to do to find delta H in this case, you would just say energy of product minus energy of reactants, and that will give you your delta H. So that's enough. So we actually showed you how you find delta H without the graph where you work from bond energies. And then now we also show you how to find delta H when you have got just the graph given to you. That's it.
Okay, that's it.
Okay.
Gift. Another question is from that guy.
Oh, who is that guy?
That guy.
Yeah.
That's the name. That guy.
That guy.
So
yeah.
that guy says, how do I see that the energy is absorbed or released on question 1?
On question 1.
Yes.
Okay, so going back to question 1 again. Now, when you calculate, let's go back and look at this calculation here. That guy, when you have calculated, you've done all this calculation here, and you come to this point and you find that your answer, it's a positive answer. A positive answer would tell you that the overall energy has been absorbed by the system. Now, if a system absorbs the energy, if it takes in the energy, that process, that chemical reaction is actually an endothermic reaction. That's why we said this is endothermic. So for you to note how energy has been absorbed, you can only tell from your calculation. You have to do all these things, starting from there, follow up these steps until you get to the end where you find your answer. If we found the answer to be negative, for example, we would have said the reaction, that process, that chemical change is an exothermic reaction. Okay? Why? Because it would have told us that overall the energy has been given off by this system. That's how you can tell. Right.
Okay, another one. Why is delta negative? Or he says, what if delta is negative? Then what happens?
When
delta
you calculate for delta H and you find it to be negative, what do you conclude? It means the chemical reaction is an exothermic reaction. That's what it means.
Okay.
It means that overall energy has been given off to the surrounding, given off to the environment.
All right, that was from
Yeah.
Javulo Brian.
Okay.
Wendy, she's a newcomer, but she's active already.
Yeah.
She says, does the catalyst only affect the activated energy? By the way, I'm enjoying the show, even though in my school we're not yet there, but I do understand. I'm going to surprise them.
What's happening?
Boom.
Yeah. Good. Yeah, so she's going to surprise them. Okay, the question is,
Does
why?
the catalyst only affect
I mean,
the
does the
activated
catalyst
energy?
only affect the activation energy? The answer is yes. It only affects the activation energy. It doesn't change any other thing around the energies that are involved in that chemical reaction. Remember, we looked at several types of energies. The bond energy is never affected by a catalyst. Okay? The heat of reaction, or delta H, is never if affected by a catalyst. The only energy affected by a catalyst is the activation energy, because a catalyst comes in to lower it down, making it easier for the reactants to quickly have that minimum energy required for them to react. So if, for example, some reactants needed 100 kilojoules per mole for them to react, the catalyst may come and say, at least let's lower it down. Let's make it 92 kilojoules per mole, so that more and more of those molecules can be able to be at a state where they can be able to react, because you need energy to be able to react. That's what it is all about.
Okay, last
Yeah.
question, last one
Yeah.
from Kamogelo. I need help. What are the two industrial applications of exothermic reactions?
To industrial, it's not about industrial application. Whatever chemical reaction that takes place, we can classify it as either exothermic or endothermic. So even industrial processes, like, for example, the contact process where you're producing sulfur trioxide, that process will give you, or it will have, an activation energy, would have overall change in energy. We will classify it as either exothermic or endothermic or Haber process or whatever. As long as we have a chemical reaction, we will either be having it as an endothermic reaction or an exothermic reaction.
All right.
Yes.
Well, thank you so much, sir. That's where we end it for today.
Thank you, Abraham. I think and I hope that the mindset has enjoyed the lesson.
Indeed. Well,
Yeah.
guys, remember, whatever you have learned today, it's not just for today. You'll keep it, and it's going to be useful even on your exams and beyond, even in matric. I believe this will help you too. But otherwise, in case you miss our schedule and our notes, go to learn.mindset.co.za. We love you, and we're leaving you in peace.